Hi there, and welcome to Chapter 1 from Stevens's Matrices, Vectors, and 3D Math. In this chapter, we're going to do an introduction to linear algebra. Now, linear algebra is actually a huge field of mathematics. We're just going to cover some of the basics that are required to solve systems of equations and to do some geometric manipulations in 2D and 3D. In this video, we're just going to do Chapter 1.1, and we're only going to do half that. It's a pretty long section, so we're going to do half of it here and then half in the following example. So before I get started, I'm going to switch this to full screen mode. There we go. Okay, so in this section, we're going to deal with systems of linear equations. So it's worth defining a couple of terms in here. First, let's look at this word linear, a linear equation. And let's look at this example. All right? If you have this equation, and you've seen equations similar to this probably in the course of various high school algebra classes, oftentimes you would be asked to solve for x. Now the problem is, if you were to try that, you'd run into some issues, right? First, you have an x to the fifth up top here, right? X to the fifth, right? So that's a little bit of an issue, but we can take a fifth root and get x by itself. But the problem is we have another x right here as the argument of this sine function. So when I want to solve for x, that means I want to have x equals, and I'll have some stuff over here, and that stuff will not contain any x's, right? And in this particular problem, you actually can't do it. You know, after all those years of high school algebra, where you could solve for the variable, in this case, you actually can't. You have to use a numerical method, right? And that's because this equation is not linear in x. On the other hand, if you were asked to solve this equation for y, right, y equals some stuff, and I don't want any y's on the right-hand side, that's actually a lot easier. Because I have a y here, it's multiplied by a negative 72, but that's okay. It's not raised any powers other than 1, and there's a y here as well. So I'd get the y's onto one side, the x's and the constant to the other, and eventually I would be able to get y equals, and there'd be a bunch of stuff over here with the x's, sine x, x to the fifth, and 105. But you'd be able to solve for y, and the reason you can solve for y is because y appears linearly in this equation. Right, so that's what we mean by a linear equation. And the second term here, a system of linear equations. That means we're going to have more than one equation. And we'll do these examples down here. Right? So example 1, we have a system of linear equations in the variables x and y. And if you want to solve this system, that means you want to find the values of x and y that satisfy both equations. So there's a lot of things going on at once. And you may or may not have seen situations like this in algebra. So we're going to do example 1 here. Let's go to example 1. Okay. So probably the most common way to do this would be to solve one of the equations for one variable, stick it into the other equation, and then that would only have one variable in it. And what I mean by that is, suppose I took this first equation, and I said I'm going to solve this for x. X equals 4 minus y. And then I would substitute that into the second equation. So I'd have 3 times 4 minus y plus y equals 4. That would give me 12 minus 3y plus y equals 4. Let's see, that'll give me negative 2y. Subtract 12 from both sides, I get negative 8. And then y equals negative 8 over negative 2, which is 4. So we're halfway there. We found one variable. Now to get the other variable, we can take this value of y and plug it into really either one of these equations. But the easiest one to plug it into, we actually rewrote up here. So x equals 4 minus y, but that's y is 4, so x equals 0. And so we have solved this system of linear equations. X equals 0 and y equals 4. And you can always check your solutions. You can always say, all right, if x is 0 and y is 4, is this first equation satisfied? It sure is. And then if you go to the second equation and you let x equal 0 and y equal 4, again, those values satisfy the equation. So we actually found a solution to our system. There's one other way you may have seen this. You may have said, all right, I'm going to just start with these two equations here. And I'm going to take the first equation and I'm going to subtract the second equation. And that way my y actually disappears, right? So that's going to be x minus 3x, that's going to be negative 2x. Y minus y, that's gone, equals 0. So I'd get x equals 0. And then you plug this back into either one of these equations. We'll do the first one. So we get 0 plus y equals 4, or y equals 4. So either way works. There's the solving for one variable and subbing it back in, like we did over here. Or you can actually manipulate the entire equations, adding one to the other, and reduce the variables in that scenario as well. So that's great. We got a solution. Right? If, on the other hand, we go to that second example, let's see, this one. So in this first example, we did get an answer. Right? X equals 0 and y equals 4. If we consider our second example here, I have a page for that as well. I'll go through the same process. I'm going to solve this for, say, x. X equals 4 minus y again. Plug that back into this equation. So I get 3 times 4 minus y plus 3y equals 12, which gives me 12 minus 3y plus 3y equals 12. All right, and so the first thing you should notice is that my y's disappear, and I get 12 equals 12. So this is saying, for what value of y does 12 equal 12? Well, any value. The y disappears. It doesn't matter what you put in. So we know we have infinitely many solutions, right? You can choose any value for y that you want, but you do have to make sure that after you pick y, you make sure that x equals 4 minus y, because that constraint is still required, right? All right, so y would equal anything you want, and then x would equal 4 minus y. So we have infinitely many solutions. But there is some structure to that infinitely many. All right, so we go back to our 3 examples. So this particular system of equations has infinitely many solutions. Infinitely many solutions. All right, so let's take a look at our third example here. I have that on this page right here, example 3. And again, looking at it, it looks pretty similar. So I'm going to do the first equation, solve it for x. Plug that into my second equation, so I get 3 times 4 minus y. Doesn't equal, I forgot my plus in there, plus 3y equals 10. So I get 12 minus 3y plus 3y equals 10. Again, my y's disappear and I get 12 equals 10. So this equation says, for what value of y will 12 equal 10? Well, no value of y. There's no value of y that's going to make that work. So in this case, we have no solution, right? No solution. Right, and these were actually pretty straightforward examples. They weren't too complicated, and you couldn't tell by looking at them the structure of the solutions. But what we had here was a unique solution in the first case, infinitely many solutions in the second case, and then no solutions in the third case. Right. And if you think about that, these equations are actually just equations for lines. And so what we're asking for is what is the point of intersection between two lines. In our first case here, we had two lines. They intersected at a point. In our second set, we actually had two lines, but they're the same. So I had infinitely many solutions, right? And if you look at this, you can sort of spot it. If you look at example 2 here, if you take that first equation and multiply it by 3, you get the second equation. So there's actually only one equation there. It's the equation for a line. And then in this case, it's not immediately obvious, but we don't have any solution. So that's something to keep in mind when we're solving systems of linear equations. We can get a solution, we can get infinitely many solutions, and we can get no solutions. All right, so what we're going to do here is we're going to come up with a method. We're not going to come up with it. It's already been very much developed. It's called Gaussian Elimination. It is a sequence of procedures that are used to solve systems of linear equations. Right? And what's nice about this procedure is that if there is a solution, it will always find it. Right? And if there are infinitely many or no solutions, that determination will be made along the way. So the way we get started with Gaussian elimination is we start with a system of equations. Right? And my variables in the last problem were x and y. And if I had 3 variables, you could call them x, y, and z. But just to demonstrate that you can make this as big as you want, the variables will just be denoted x1, x2, and x3. Right? So we have our system of equations. We have 3 equations, 3 unknowns, 3 variables. And what we're going to do is we're going to turn this into an augmented matrix. And all the augmented matrix is a left portion which contains the coefficients of the variables in the appropriate order. For example, this 2 comes from that 2. This 6 comes from that 6. Right? And this 1 comes from the implied 1 sitting out in front of that x2. Right? And then the right-hand side of my equations goes on the far right of this augmented matrix, and we put a line to delineate the two. There's the coefficients and then the right-hand side. And then we're going to solve this through a sequence of row operations. And specifically what this does is it allows us to work on this augmented matrix, and we don't have to keep writing and rewriting all those variables. Right? So here's the trick to Gaussian elimination. Right? We're going to start with this augmented matrix that looks like this, right? And through a sequence of what we call row operations, we want to convert that into an augmented matrix that looks like this. And that form is called row echelon form. And the key thing to notice is that I have 1s along the diagonal of the coefficient portion of the augmented matrix and 0s below that diagonal, right? And we're going to do this with a sequence of row operations. So we're going to start here, and we're going to end up there, hopefully, if we can do it, right? And then afterwards, we'll be able to use a process called back substitution to solve for the variables. So here's how we're going to do this. We're going to do this with row operations, right? So there's only 3 we have to worry about. You can take any row and multiply it by a number, right? And we're going to denote that with this format here. Row I will become some number A times row I. And really all we're doing is taking one of these equations and multiplying it by a number. And whenever you multiply an equation by a number, you have to remember to multiply both sides. Right? So when we multiply one of these rows, we're actually just multiplying both sides of one of the equations. We can also add or subtract a multiple of one row to or from another and replace it. That will be denoted by this symbolism here. Row I will become row I plus or minus some multiple of row J. Right? And then the final row operation, it's one of my favorites, it's the easiest, is you can just switch any 2 rows you want, right? And that's quite simple. That just says, all right, if I want to solve this system of equations, I can list them in that order, or I can switch the order. Right? It doesn't really change the system. Okay, so let's see this in an example. We're going to do example 1 here. And I start off with this system of equations. Right? Pretty nasty. There's hardly any zeros in there, so we turn that into an augmented matrix, which is filled with numbers, right? And now what I want to do is I want to get that row echelon form, right? I want to get ones here, zeros down here, and then some other stuff up here. All right. So the first thing, I want to work from the top left to the bottom right. So the first thing I want that 2 right there to be a 1. So I'm going to take row 1 and I'm going to multiply it by 1/2. So that means when I take this 2 and multiply it by 1/2, I get a 1. But I have to do this to the entire row. So I multiply this 4 by 1/2 and I get a 2. I multiply this 6 by 1/2 and I get a 3. I multiply this 18 by 1/2 and I get a 9. And then I'm just going to copy the next 2 rows verbatim as they are. Okay, so I've got my 1 in the top position. I've got that 1. That's what I wanted. So the next thing I want to do is I want to get all zeros below it. Specifically, I want that 4 to be a 0. So what I'm going to do is I'm going to multiply this first row by -4, and then I'm going to add it to the second row and replace it. So when I take -4 times that 1 and add it to 4, I get this 0. And that's actually why I chose -4 as my multiplier. But again, remember, you have to do this to the entire row. So if I take 2, multiply it by -4, I get -8, plus 5 gives me -3. 3 times -4 is -12, plus 6 is -6. And then 9 times -4 is -36, plus 24 is -12. Right? So in getting this 0, I've changed the entire second row. So I got my 0, but it changes the whole second row. Okay, so I'm going to go back up to this first matrix up top, and what I want to do is not only do I want to get the 0 here, but I want to get a 0 where that 3 is, right? I want zeros below that 1. So that 3, I want to get rid of that, turn it into a 0. So I'm going to take my first row, multiply it by -3, and add it to my third row. Right? So when I take 1, multiply by -3, and add it to 3, I get 0. I take 2, multiply it by -3, and I get -3. No, I don't. 2 times -3 is actually -6. Sorry about that. Plus this 1 gives me -5. 3 times -3 is -9, plus -2 gives me the -11. 3 times 9 is -27, plus 4 is -23. So through that particular row operation, I was able to take this 3 right here and turn it into a 0 right here. But it affected the entire third row. Okay, good. So I'm getting there. I have my 1 in the top left position and zeros below it. So now I'm going to move to the right and down 1. And I look at this -3 here. And what I want that to be a 1. So I'm going to take this row, and I'm just multiplying it by -1/3, or dividing it by -3, whichever one. But again, you have to do that to the entire row. So when I take -3, multiply by -1/3, I get 1. That's why I chose that multiplier. When I take -6, multiply by -1/3, I get 2. When I take -12 and divide it by -3, I get 4. So I got that 1 in this position. Right? I got my 1 right there, which is where I want it. These are called pivot positions. Okay, so things are looking pretty good. What I really want now is I want a 0 below my 1. So I'm going to take this second equation, multiply it by 5, and add it to my third equation. When that happens, I'm going to take 1 times 5, add it to negative 5, and I get a 0. That's why I chose 5 as my multiplier. But I have to do that to the entire row, right? So I have to take 2 times 5 is 10, add it to negative 11, and I get negative 1. Then I take 4 times 5, and I get 20. I add it to negative 23, and I get negative 3. Right? Okay, so things are looking pretty good. I'm almost there. I have a 1 with zeros below it, a 1 with zeros below it. And now I just need to get that to be a 1. That's easy enough. I'm just going to take this third row and multiply it by negative 1. That changes my negative 1 to a 1 down here. It changes my negative 3 to a 3. And notice at this point I am now in row echelon form. I'm not, the augmented matrix is. And here's where Gaussian elimination stops. Right? I got it to row echelon form. And here's the beauty of row echelon form. I can now, through a process called back substitution, get all of those unknown variables. For example, if you take that third row, the equation that that represents is just x3 equals 3. So good. I already have x3. Right? Now if you take this second row, so we're going to work backwards, right? We got our last variable, x3. Now we're going to work our way back. That's why it's called backward substitution, or back substitution. So I look at my second row. That represents this equation, right? And so if you rewrite that equation, you have it right here. But I already know what x3 is. x3 is 3. So that becomes this equation when I plug it in, and I get x2 equals negative 2. And now I'm going to back up to the first equation. And when I write that here, it has x2s and x3s, but I know what x2 is. That's negative 2. I know what x3 is. That's 3. When I plug those in, I get this equation. And then I just solve for x1, and I get x1 equals 4. Right? So our solution is x1 equals 4, x2 equals negative 2, and x3 equals 3. I solved the system. Now it's easy enough to go back. It's actually not easy. It's sort of tedious. It's not complicated, but it's tedious. I can go back and check these answers pretty easily. In the sense that if I go back to my very first system, I have 4, negative 2, 3. So my x1, so I'm going way back here to my very first system. If I let x1 be 4, x2 be negative 2, and x3 be 3. Right, those are the answers. Let me just confirm. Yes. And so if you put that in, if you put those in there, for this one, first one you'd have 8 minus 8 plus 18 equals 18. It checks. Right? That's what we mean by solving the system. If we put those variable values into the second equation, I'd have 16 minus 10 plus 18, which is 24. Check. And if I did that to the third equation, right here, I'd put a 4 in for x1, so I'd get 12 plus negative 2 minus 2 times 3, which is minus 6, and I get 4. So check. So that's what we mean by solving the system. We found the variables so that when you plug the values for those variables, it satisfies all of the equations, right? So it's significantly more complicated than solving a single equation. Right? But we did it. We got a solution by Gaussian elimination using row operations to get it into row echelon form. And then we use back substitution to get the variable values. And so I'm going to stop here. This video is already pretty long as it is. And then we'll pick up and we'll do another example, show how things can get a little messy with no solutions or infinitely many solutions. But that'll take place in the next video. So we're good for now. I bid you farewell.